Tim is a postdoc and HPC administrator at Johannes Gutenberg University in Mainz. In 2011, he received his PhD from University of Paderborn. His research focuses on HPC storage file systems and automatic parallelization. Tim Süß, ladies and gentlemen.
Wow, this looks great. Okay, today I would like to talk about our research project where we provide QoS, quality of service management, for Lustre, where we use the token bucket filter, which is installed in the NRS of Lustre. And since I'm here for the first time and we think to participate in the Lustre community stronger in the future, I would love to introduce our university at first. And then, Mainz is the capital of Rhineland-Palatinate. It's quite close to the Rhine. It's near to Frankfurt. It is founded short before Christ, and it's also famous for its wine, but I'm not sure about this. I was only told this. And we have, I don't like wine, sorry. We have some experiences in industrial storing data because the Gutenberg Bible was printed in Mainz, so 500 years ago we already made industrial storage. And by accident, the University of Mainz was founded in the same time frame. And nowadays it has about 35,000 students from 150 nations. Has many different departments, and we do research in different areas in particle and hadron physics, material science, life science, and so on and so forth. So we have very many use cases, and we provide HPC systems, clusters, MOGON. And MOGON, this is our first cluster. This consists or provides 35,000 cores, and was installed in 2012. And it has a file system of about 1 petabyte and achieved 300 teraflops. And this is a nice picture of a MOGON, our new cluster. Or the first stage is not that nice. For this reason, we placed our administrator in between our racks. But this cluster is significantly smaller, but achieves significantly better results. And so it has about half a petaflop, and this is the first stage. The next stage will be delivered in the beginning, at the end of this year. And here we run a 5 petabyte Lustre system, which is provided by NEC. So, is not what I was invited here. I'm invited here to talk about quality of service management in HPC and why do we need, and at first I will tell you why we need quality of service management. Then I will tell you a little bit about the architectural approaches. And then I also will present some results and scenarios. So, when we look into file system in HPC systems, we see this burstiness in the accesses. And most administrators will tell you they don't like this. Because this, on the one hand, shows that your file system is too big in some situations, and in some situations it's too small. So we really would like to see a flat curve where we always use the maximum of the bandwidth and where we utilize our file system the best. And also the users have a high demand on quality of service because in our situation we have some departments that spend additional money for the storage. And they get more storage, they can store more data, but they do not get more bandwidth to access the storage. And they really need this bandwidth because they only rely, their results only rely on this, the bandwidth. Then we have a lot of malicious users that attack somehow the file system because they have many small files and they slow down all other users. So we need some mechanism to punish them. Sorry, I didn't find another word. And another scenario is checkpointing. Sometimes we have really this burst where we have to write a lot of data in a short period of time, and this can overload our complete file system for a short period of time. And this prolongs the complete runtime of the jobs, and this is not that nice. So we would love to have quality of service management, where a user can say, I want to have this bandwidth for read and for write, and we want to guarantee this. And we would love to do this on file base. This would be nice. But therefore, we have to include several aspects in our architecture, for example, the batch system, and also the Lustre client and servers. And I will talk always about Slurm here, but this also will work with LSF or other batch systems, okay? So our situation is as follows. We have our Lustre environment with our clients, our management and metadata server, and our OSSs. And we add some components here. We add our quality of service planner, and we have already Slurm, and we have to modify it a little bit. In other words, we have to provide a new plugin. Additionally, we have to bring some new features to the OSS, but these are only servers that set some parameters. They run beside. They are not integrated directly into Lustre. So our first approach was, we wanted to do everything on file base, because some users want to read some files really fast, some files are not that important, or we just need a few bits from these files sometimes. And for this reason, we want to regulate the quality of service per file. So here we can see each OST as a resource with a certain bandwidth, and we can see them somehow like cluster nodes that have some resources what are shared among different users. Here the users are jobs. So it should look like this. We have a user that submits a job with a job name foo compute. He wants to use some resources, and he wants to start this on a specific file, foo bar here, and he wants to have a bandwidth, an I/O bandwidth of 10 gigabytes per second. Then this request is submitted to our QoS-Planner. The QoS-Planner asks the MDS what are the responsible OSTs, and then we can schedule the requests here. If there's enough bandwidth available, or if we can fulfill the request, then we acknowledge Slurm and set the policies of the network request scheduler on the OSS. So this was our first idea, but this idea has two big problems. At first, this does not scale. This does not scale if we have too many files that are accessed, does not work. And another big problem is the scheduling does not work anymore, because in the new Lustre version, we have the situation that the stripe size can grow and that we do not know the OSTs in advance. But we have to guarantee the bandwidth on these OSTs. This does not work anymore. For this reason, we changed our approach, and we said, okay, we do not care about files anymore, we just care now about OSS. This is our first phase. This is a research project. So let's look what we can do here. So we keep everything almost the same. It's almost the same. We have our Slurm that talks to a QoS front end. This is talking to the server, and the planner is talking to the Lustre backend system, and controls here everything. And the information what are provided from the planner and from the scheduler are somehow monitored, and so that we in this way we guarantee bandwidth. So now, how did we do this? The integration in Slurm is really simple. It's really simple. We can see bandwidth as just as a global and a local resource. Why do we need two resources for one feature? Because we have an overall file system performance, and we have the bandwidth on each node. Each node provides you 5 gigabytes per second, but the bandwidth of your file system might be 100 gigabytes per second, and this has somehow to work hand in hand together. For this reason, we said, okay, the global available bandwidth, we treat them exactly as licenses, one license per megabyte. You have to get one. And the local bandwidth is treated as a generic resource. And we wrote this. And here you see such a call, and it works quite nice. It's really simple. Users can make use of it. Then we need the token bucket filter, and most of you are familiar with the token bucket filter, but nevertheless I will introduce it quickly. We have incoming requests. They are classified, and depending on the classes, we have tokens available, and for each request we need one token. If a token is available, the request can be processed. Otherwise, it is delayed until a new token is available. Okay. The TBF token bucket filter is implemented in the network request scheduler, as I already mentioned, and we say one token is approximately 1 megabyte. So, and we have different classes. We can classify this request by job IDs, user IDs, processor names plus user ID, process names plus user names. But this token rates, how fast token reappear, can be set from the administrator or from the batch system in our case. So, but we have two situations. DDN made a great job by integrating two features to enable the throughput from multiple flows and the proportional sharing spared bandwidth. Here we have such a situation where we use the throughput for multiple flows. Here we have 16 jobs, and the different jobs occupies or request different amounts of IOPS. And there are in the first line you see 15 wants to have 10 IOPS, and there's one job that wants to have 10,000. And instead of saying, okay, we cannot provide 10,000, everything is scaled down. Also the 10 IOP jobs. This is somehow against our quality of service management because we slow down the jobs by other jobs. On the other hand side, it is possible to proportionally share free bandwidth between jobs. Here we have the situation, we have 16 clients in per job, we have 2 jobs, and one job wants to use 150 IOPS, the other one wants to use 100 IOPS, and we have 500 available. So we scale both jobs so that we occupy the complete bandwidth. But this is bad for the user, because he has no idea how long his jobs really would take, so he cannot plan for the future. This is the administrator's point of view. There's no learn curve for the user. And next time he says, oh, my job was this time so slow, and then you have to explain this to the user. So, okay, we have now this component, and now we put everything together. We integrated it really in our test system. For this reason, I like this T-shirt, what is given outside. We really do our tests in productive systems. But our administrators or head of HPC had some limitations. He said, okay, you're allowed to set the policies on the Scratch device. Only on the Scratch device, and there are 2 OSSs, and in total 10 OSTs. And you're allowed to set the policy token bucket into job ID, and the job ID var is set to proc name, so the processor name, process name plus the user ID. And on the system we have the TBF filter version of 2.8, because for stability reason we cannot integrate the fast newest version. Our administrators have there some concerns. And also on the client we set this job var ID. And here we were able to reserve with our Slurm plugin bandwidth a priori. This means when we submit a job, we say, okay, we need for the complete job runtime this bandwidth. And therefore we have a little client program that just reserves a throughput, here in this case of 100 for 100 seconds for a certain folder to determine the OSS in later versions, and in a certain job ID to identify the job later. This program is called by the Slurm plugin. And then Slurm handles automatically the licenses and the local resources. This is the first step because in this case, everybody has to provide bandwidth, his bandwidth needs, and he can say whatever he wants. And we want to couple this somehow with the users management of Slurm itself, because there are users that spend more money for it, and so they should benefit from it. Additionally, we can throttle down malicious users only by setting one variable in our environment. And another feature, what is nice, that is we can credit users. Users that return their reserved bandwidth earlier as expected, they can have a benefit from this because they are good for the community, so they get more credits in the future. This would be a possibility. But this situation is in HPC systems rarely the case. Usually, for such a reservation, it would be necessary that you have a data flow over the complete application one. Otherwise, you reserve bandwidth and you do not use it. This is bad. For this reason, we provide an interface for spontaneous reservation because most applications have few I/O rates. They have in the beginning, and they read their input data, then they process, and they write some checkpoints. Maybe they read a little amount of data, and at the end, they write a lot of data again. So we wrote an C++ API for spontaneous I/O accesses, and here you can reserve bandwidth for a certain time span. You can test if the reservation is available, and you can remove your reservation if you're done. And these are the most important functions. You can add reservations asynchronously, so you can say, okay, I need this bandwidth, and when it's available, I will use it. And you can proceed with computing. Otherwise, you can also block you can do your reservation asynchronously, so your program blocks until the reservation is available. And you can remove reservations, and you can, of course, you must be somehow able to test your reservation if you do it asynchronously. Why do we need this? When you do your reservation, we cannot say in advance when your reservation will be available, because we have a backfill scheduling. And every time a job is finished earlier than expected, everything is moved to the front. And this causes that when we say you can start in 5 minutes, maybe the time frame has already vanished because it was shifted to the front. So we need, have this test reservation function, what is used. And this feature can be used really good by applications like, for example, Espresso++, and here we also tested it. And in Espresso++ is a molecular dynamics simulation. Or in other tools like SCR, this is a checkpointing tool from Lawrence Livermore. And those tools are able to say, okay, I want to write a checkpoint when the resource is available, when the file system is available. We can delay it for a while. And here we can exactly use this feature. And here we have an example from Espresso++. They have this dump XYZ QoS method, and this simply checks if there's already if data has already been written, if I need a new reservation. If this is not, if I'm not waiting to write the data, I start a new reservation and gather my data for checkpointing, and then I just proceed. And then I check simply, is the reservation now active? And if this is the case, I can write the data. Otherwise, I do my next simulation step, and I look later if the reservation is available. So we have tested this in our system, and sadly, I cannot show you real results until now, but it's working quite nice. We have integrated it in Slurm, but as I said, it should be possible for other batch systems too. And it is not only for Lustre, most probably it will also work for other distributed file systems that provide something similar to the token bucket filter. And that's all from my side. Thank you very much, and I'm here for questions.
So how does a user figure out how much I/O they need, or how do they know how much they should request?
This is another extension what we can think about in the future to add some artificial learn mechanism or machine learning algorithms that learn over the time this application with this input takes this much. But at the moment it's pure experiences. And I know that our partners from DDN are working on this, right?
So to answer that last question, I mean, you might be able to use the job ID statistics.
Sorry, I did not.
The job ID statistics that are captured and stored on the OSTs. You know, after a job completes, you might be able to take that and submit, you know, put it in a post email for each job that says, hey, your job used this much I/O. And
this is good suggestion to learn over time how jobs behave. Yes, because most jobs behave similar, but not always the same, because the runtime depends on the input quite often. But this is a good starting point. And maybe with machine learning algorithms, at the moment everybody's talking about machine learning, what it can do, and it's not.
And do you have any plans to add hooks for this into SCR?
Sorry,
right?
I didn't.
Do you have any plans to add, like submit a patch for your scheduling to the SCR, like scalable checkpoint restart library?
First, we are in close contact to Catherine, who's developing it, and maybe we will do it in the future. But first, we must have a perfectly running system where we really can test it. At the moment, it's a research project, and in the next months, I will rewrite a lot of code because the main developer in the past, Jürgen Kaiser, has moved to SAP, and I took his job, and now I have to write a lot of things new.
Thank you.
Thank you. Thank you.